Good day, everyone. So today we're going to go over section 12.2, and we're going to start with calculating a test statistic. So the hardest thing about calculating test stat is that it's not the calculation itself, usually. It's actually knowing your symbols. So you got to know what p hat is, you got to know what p is, you got to know what n, s, x bar, mu. If you haven't memorized those things, it's time to memorize because if you don't know those symbols, you're not going to be able to put things correctly um, into the formula for the test statistic. Okay, and it's going to be easy to switch things around. All right. So remember this formula back in chapter 2. We had this formula where we had oh, I don't have my pen yet. There we go. We had z is equal to the observed value minus the mean divided by a standard deviation. Well, we've been replacing standard deviation with standard error. So you could think of this also as a z-score, okay, and putting the standard error in there, all right? And so that means that the formula when testing the population proportion p. So here's what you got to remember is that the formula for a test statistic will change depending on what you're testing. This formula is only good when testing the population proportion p. So we're going to have a different formula when testing mu. All right. So here's the test statistic, and I'm just going to put this on the next page. And the first place I want to start with is this, is that I put a little TS here to stand for test statistic. And I do that because I don't want you to mix this up with the critical value. These things are not the same thing. That's why I put a little TS there versus a little CV there. Students see in textbooks that don't write little symbols here for the test stat and the critical value. They think that they are equal to one another, and they substitute one for the other one. No, they are not the same. These are two separate concepts. All right, these are two separate concepts. So please do not substitute one for the other one. That's the first thing. Second thing is that let's make sure we know what the symbols are throughout this formula here. Let's go with the stuff that we already know. P hat is the sample proportion. N is the sample size. We knew those things. What in the world is P sub 0? Okay, this is a sub 0. All right, sub 0, sub 0, sub 0. All right. What is P sub 0? P sub 0 is the value in the null hypothesis. All right, it's the value in the null. So where else have we seen the idea of sub 0? So what the book is trying to do is remind you where this is coming from. So remember that the null is the symbol for the null is H sub 0. So what they're trying to do is remind you, they're trying to do you a favor here, that they're trying to remind you that, oh, when you have P sub 0, that's just the value that's coming from the null hypothesis. All right. So here's a problem. A researcher wants to test the proportion or the percentage. Actually, I'm going to stick with percentage here because eventually I have percentage down here, of U.S. drivers that drive a foreign car. He randomly samples 100 U.S. drivers and 45 drives a foreign car. Test at the 5% significance level if the percentage of all U.S. drivers that drive a foreign car is greater than 40%. Okay. So what's P hat then? P hat, remember, is X over N. X is the number of successes. What's a success here? We find a driver that drives a foreign car. We had 45 of them. The number of successes is X here. Divide by N, that's 100, and so we got 0.45. So we know that 45% or 0.45 of our sample of 100 US drivers drives a foreign car. N is the sample size, and that's 100. We knew that. So what is P sub 0? Well, remember, that's the value in the null. And since we were testing greater than 40%, all right, we have here in the alternative, P is greater than 0.4. Now, you could put 40%. I don't care. Okay, so you could have put P is greater than 40%. I'm good with that. I just went ahead and put it into a decimal form. Either one is acceptable. So what's going to be in the null? P is equal to 0.4. All right. So that means whatever values in the null hypothesis, that's P sub 0. Well, what's in the null hypothesis? 0.4. All right. So P sub 0 in the formula, in the test statistic, would be 0.4. Now, before we actually calculate the test stat, I want to point something out to you. Usually what happens is that these problems that will be given to you, a little bit of background information is given to you. So that's why I put some parentheses right now around the first sentence, all right? And then what's going to happen is that somewhere in the problem, it's going to talk about the sample, okay? And so notice he randomly samples 100 US drivers. And so your brain should automatically go, oh, okay, now we're talking about sample stuff because we need our data to be summarized for us. Remember, we're not going to give you the raw data here, all right? We're just going to go ahead and give you some summarized data. That's what we did here. And you got to know, okay, that's sample stuff, all right? So let's label that correctly. P hat, N, sample proportion, sample size. And then notice it says test. And so it's going to tell you then, well, what exactly are we testing? All right. And so test a percentage or a proportion, and we're going to test that it's greater than 40% or 0.4. All right. And so those are kind of your three key components when you do these problems: background information, sample information, and then what are we testing? Okay. So here's the test statistic. I put all the values in here, and you can go ahead and calculate it yourself if you wish, but I came up with 1.02. 1.02. And we should go ahead and interpret that. Now, if you had problems putting in your calculator, that's how you go about doing it. All right. Some of my other students in other classes, they sometimes have problems. I doubt that you're going to have problems, but if you want, there you go. All right, that's how you put it into your calculator. And I'm more concerned about, can you interpret this? All right, what exactly does this mean that we got 1.02 for our test statistic? And what I want to emphasize here before I start is that this was a positive 1.02, because your test statistic can also be negative, right? Z-scores can be negative, and so let's interpret. This means that our sample proportion, right, our p hat is 1.02 standard errors, because remember, Z-scores are in terms of standard deviation or standard errors, right? And is 1.02 standard errors above, because we had a plus sign here, what? The value in the null, because that's what we were comparing to, okay? So there is our interpretation of the test statistic, okay? Now the only thing, well, actually there's two things that I want to discuss here, okay? There's two things that I need to discuss with you. Is that one, why did we say P sub 0 is I'm going to go back here. Why did I say, I'm going to go all the way back to this guy right here. Why did I say that P sub 0 is the mean? Okay, so for every hypothesis test, we temporarily assume that the null hypothesis is true. And so basically what we're saying is that we have an assumption for the value of P. And remember, the value of P goes right in the middle of the center of the sampling distribution of P hat, right? And so we have an assumption for the mean of the sampling distribution for P hat. And for this problem, it happens to be what? It happens to be 0.4, okay? Happens to be 0.4. So that's why we throw that in for the mean, okay? Second thing to note is, notice the standard error is a little different here than it was for the confidence interval. Again, since we have an assumption for P, and remember the formula for the standard deviation for the sampling distribution of P hat is P times 1 minus P divided by N, all right? Since we have an assumption for P, we're going to use it here, okay? That is different than the confidence interval. Remember, the standard error for the confidence interval used P hat, okay? So please note that difference there between the two, all right? So let's now learn how to calculate a p-value. So we'll get to answering the question, what was the p-value for 1.02, but let's kind of build up to that point, all right? let's actually start with a left-tailed test because that's the easiest thing to do. So why did I say this is a left-tailed test? Is because we have a less than sign in the alternative. So remember, that's a left-tailed or lower-tailed test, okay? So you need that bit of information. I told you that we were going to use that information somewhere. It's now, all right? It's calculating the p-value. And the test statistic turned out to be a negative 2.51, negative 2.51. So we need that basic information there, all right? So we have a left-tailed test. Test stat is a negative 2.51. So how are we going to figure this out? How are we going to figure out the p-value? Well, since the test statistic is in terms of z, what that's telling us is go look at the standard normal table for the p-value. If this was in terms of another probability distribution like t, which is going to be the case when we calculate the test stat for mu, we would use a t-table to figure out the p-value, okay? So what I'm telling you is you cannot always use the standard normal table to figure out a p-value for every possible problem, okay? And when you're doing a hypothesis test, that you only are going to use the standard normal table when the test statistic is in terms of z, all right? So I went ahead and drew that. Well, I had the computer draw it anyways. So here's z, okay? Negative 3, negative 2, negative 1, 0, 1, 2, 3, right? And here's a negative 2.51. And I had the computer shade to the left of a negative 2.51. Why did I do that? Because we have a less than sign here. We have a less than sign. And so what we're doing is we're figuring out the area to the left. It's a left-tailed test. That's why we call it left-tailed. So we're going to figure out the area to the left of the test statistic, okay? So notice our area is not too big, okay? So this area in red is representing the p-value, all right? So what I'm going to do is I'm going to get out of the presentation and I'm going to go look at a standard normal table to look this up. So negative 2.51. All right, let's go look this up. Negative 2.51. So here's my standard normal table. And negative 2.51. All right, so now remember, before we just blurt this answer out, all right, you got to remember that the standard normal table, at least the table that I've given you, is always giving us less than. It's always giving us less than. And we were trying to figure out what is the area to the left of a negative 2.51. And so when you have a left-tailed test, all you got to do is look it up on this table and you're good to go, because this is basically always giving us the area to the left of the value of z. So a negative 2.51, I got here 0.0060. That would be our p-value for this problem. All right. How about, I'm going to stay out of the presentation for a second. I'm just going to keep it like this, all right, so I can go back and forth between the standard normal table and the slides here. So we have p is less than 0.7, left-tailed test. Our test stat is a negative 1.68, negative 1.68. So since it's left-tailed, we just get to look it up. Now notice the p-value being represented here is a little bit larger than before, right? It's a little bit larger than before. So negative 1.68, negative 1.68, negative 1.6, and then 8 should be this number right here, 0.0465. Hopefully you found that, because remember 0.08, okay? So hopefully you found that number with me, all right? Left-tailed. How about when we have a right-tailed test? That would be like what we had in our problem, all right? So remember our test stat was 1.02, and we had p is greater than. So we have a right-tailed test or an upper-tailed test. So notice I've gone here and represented the p-value in red. And so we want the area to the right of 1.02. Okay, now you got to be careful when you go to your standard normal table. So 1.02, let's go look that up. Now remember, let's take a look at the picture here. When we look up z, it's always giving us the area to the left. but we don't want the area to the left, we want the area to the right. And so we actually want the unshaded part that's represented here, okay? And so what are we going to have to do? We're going to have to take 1 minus whatever the probability is. So let's take a look at 1.02. 1.0, and remember it's the third number here, 2. 1.0, there it is. So we got 0.8461. 0.8461. That's not our answer. It's going to be 1 minus that, okay? And so what's really our answer? 0.1539, I think, if I did my math correctly. Now, what's the other way that you could do that? You could use the idea of what? Symmetry. So if you looked up a negative 1.02, I think you're going to find that number also, 0.1539. All right, let's do one more that's right-tailed. So we got here 3.04. Now that is when I did this in StatCrunch. StatCrunch to even represent that area on the graph because it goes past 3. Not to say that it couldn't represent it. It's just that it's so small, all right, such a small area that it didn't even try to draw it. Okay, so it's going to be a pretty small number here. And so there is a p-value. It's way, way, way out here. Okay, and so this is going to be a very small number here as far as this. Remember, it's probability. Okay, it is a probability. So it is going to be a number above 0. Okay, can't be negative. Can't be greater than 1. The p-value. All right. So let's take a look what we're going to get here. 3.04. 3.04 is way down here. So 1, 2, 3, 4. I got here 0.9988, but that's the area to the left. We need the area to the right, and so we're going to take 1 minus that. So we get 0.0012, I think, if I did my math right. So I'm sure if we looked up a negative 3.04, we would get that answer, 0.0012. Okay. So again, you can either do 1 minus, okay, or you can use the idea of symmetry. Okay, how about a two-tailed test? Now, how do I know I have a two-tailed test? Because I have what? A not equal to sign here. I have a not equal to sign, so I have a two-tailed test. So remember, when I'm doing a two-tailed test, I'm testing both what? Less than and greater than at exactly the same time, all right? So here we have a test stat of a negative 1.34. So notice since I had a negative here, I'm going to go and figure out the area to the nearest tail. All right. So I'm going to figure out that area right there. However, because we were testing both tails, and you got to kind of go back to the idea of the p-value, that the p-value is getting something as rare as our test stat. Well, what's as rare as our test stat? Well, not alone is it less than a negative 1.34, what's also as rare as that on the standard normal, since we were testing both? It's exactly the opposite side. Okay, so what's as rare as a negative 1.34? Excuse me, what's as rare as less than a negative 1.34 in the standard normal table? Greater than 1.34, okay, because we were testing both sides. And so basically we have to add up these two areas, add up these two probabilities, and that would be our p-value. All right, and I would just look up a negative 1.34, and since the standard normal is perfectly symmetrical, we get to just simply double this area. And there you go. All right, so let's go look up a negative 1.34. Negative 1.34. I think it's that number right there. All right, because that's 1, 2, 3, 4. So I got here 0.0901. But that is just one of those shaded areas. We need to add those two areas together or take one of those areas and multiply by 2. And so what's really our p-value? It's not 0.0901, it's 0.1802. That's our p-value, 0.1802. How about this guy right here? So two-tailed, right? Two-tailed. Our test stat is already been calculated to be 2.78. And notice our tiny little area down here, okay? But we also need the area to the left of a negative 2.78. So notice that I went ahead and filled in that area over here. All right. And so even though our test stat is positive, I would go look up the negative side of things. Why? Because you don't have to take 1 minus anything. All right. I would just look up a negative 2.78. All right. So let's go ahead and do that. Negative 2.78, and we're going to double it. Negative 2.78. I got here 0.0027, but that's not our p-value. You got to multiply it by 2. So our final answer is going to be 0.0054. That'll be our p-value. Okay. So we got left-tailed, which is a lower-tailed test, right-tailed, which is an upper-tailed test. Then we have a two-tailed test. All right, let's get back into the presentation. And I'm waiting for, because I know I'm going to have to eventually get my pen out. So there we go. All right. So we always compare the p-value versus alpha. So once you get the p-value, you compare it to the significance level. All right. And as a reminder, if the p-value is less than or equal to alpha, we're going to reject the null hypothesis. And what we're going to say is that we have strong statistically significant evidence that the alternative is correct. Okay, but we're going to put it in terms of the problem. So let's slow down here, make sure that we understand this. This start to the sentence, we're just going to always kind of start off like this if we reject the null hypothesis. Other textbooks might say we have strong evidence. Some might say we have significant evidence, okay? We'll just say strong statistically significant evidence at this point, okay? Something like that anyways, all right? You're trying to get the point across that you have plenty of evidence to do what we're doing here, okay? Notice that I ended the quotation marks because this is in general, that we're going to put, that we're basically going to say we have strong evidence that the alternative is correct. But we're going to put it in terms of the problem, All right. So you'll see that maybe it's a little bit easier to actually see it for a problem versus just talking about it. What happens if the p-value is greater than alpha? We're going to say do not reject the null. And we're just going to add 2 words to this. We're going to say we do not have strong statistically significant evidence that the alternative is correct. So it's still, even when you do not reject the null, notice that the conclusion is still in terms of the alternative hypothesis. It's in terms of the what? The researcher's hypothesis. That's what the researcher wanted to test for that effect. Okay, and so our conclusion should always be in terms of the researcher's hypothesis, H sub A. All right, so let's go back to our problem. We have an alpha of 5%, and because I have here test at the 5% significance level. So alpha, the significance level, is 5% or 0.05. The p-value, if you went back to our problem, was 0.1539, and that's certainly greater than alpha. So what we're going to say, do not reject the null. Remember, we don't accept the null. We're going to talk about why we don't accept the null here in a little bit, okay? But we do not say accept the null hypothesis. We're going to say do not reject the null. There is a difference between the two. Seems subtle to you, maybe, but there's definitely a difference, all right? And what are we going to say? We do not have statistically significant evidence that the percentage of all U.S. drivers that drive a foreign car is greater than 40%. Some people throw in there, they would say we do not have statistically significant evidence at the 5% significance level. It starts to get kind of wordy at that point. I prefer to keep it not so wordy. Okay, I don't want you to get lost in everything. Okay, you know, I don't want you to get all tied up that I got to get all these words in here. Okay, if you get the main point across that we either do or do not have strong evidence that whatever's in the alternative hypothesis, okay, if somehow you get that point across, you know, that's what we're looking for. Okay, now why can't we accept the null hypothesis? This is an important thing to concentrate on. All right, and I play a game with my students and usually I pick out a student before class, and I chat with him or her, and I say, hey, do you have a favorite pet? And I get some basic information from that person. And a lot of times the person will say, yeah, it's either a cat or a dog. I had one person tell me a horse, and I don't want the rest of the class to hear what uh, what that student told me. All right. Uh, and then what I do is I play a game and then in front of the rest of the class. And the game is that can I guess the favorite pet of the student? And so I start off with the null hypothesis is that the favorite pet of my student is an elephant. And then I put the alternative is that the favorite pet is not an elephant. All right. Okay. And then I start asking the person questions. All right. Now, true, I already know what the favorite pet is. Okay. So I kind of cheated a little bit, but it still drives the point across here. Okay. So then I ask the student, I go, well, does your favorite pet breathe air for oxygen? Okay. Let's say that the favorite pet is a dog, and the person says yes. Okay. So everybody hears that, and then I say, well, is it warm-blooded? And the person says, yep. Does it have hair or fur? Yep. Does it have mammary glands? Yep. Does it have a backbone? Yep. All right. So basically, have I eliminated the elephant yet? Have I eliminated the elephant by the questions that I've asked? The answer is no. All these apply to an elephant. An elephant is a mammal, okay, and all these things. I'm pretty sure, going back to my 8th grade biology, that all these things apply to, or 9th grade biology, all these things apply to mammals. All right. Even an elephant has some hair underneath its chin. Okay. If you take a close look at a picture of an elephant, they got some hairs underneath their chin and their trunks. Okay. And so um, I have not eliminated an elephant. Okay. But does that mean I accept it as being true? No, I just haven't eliminated it. Well, what's also a possibility? H sub A, that the favorite pen is not an elephant. I haven't eliminated either one. Okay. So, however, if I said to the student, does your favorite animal have tusks? Well, then the person is going to say, no, it doesn't have tusks. And so, and that's what happens with hypothesis testing is basically once the hypothesis eliminates the idea that HO could be true, all right, just like I eliminated the fact that HO couldn't be true in my questions, as soon as the hypothesis test can eliminate the a reasonable possibility that HO is true, it says that's wrong and the alternative is correct. All right. Now, so you can read that, but that's basically what I say there in the last sentence. Okay. So now, if you want to have a little bit more understanding from a statistical standpoint, let's use confidence intervals to help us understand why we can't accept the null hypothesis. All right. So here's our problem. Okay. And I say, instead of conducting a hypothesis test, instead of doing that, we get rid of the last sentence. And instead of doing that, we construct the 95% confidence interval. Now, bear with me. Okay. So instead of doing a hypothesis test, we construct a confidence interval. All right. So a confidence interval, remember, we would have our critical value, right? Here it would be 1.96 since we're conducting a 95% confidence interval. And I did the math already, and it turned out to be 0.352 for the lower bound of the confidence interval. The upper bound is 0.548. So what we're saying is that we're pretty sure that P is located what? Between 0.352 and 0.548. We think P is located between those two values, okay? And so it can be any value within that interval of numbers, okay? All right, so graphically, all right, graphically, that means, these are the possibilities for P. It could be anywhere from 0 to 1, right? It could be from 0 to 1. We're saying that the population proportion P is located somewhere between 0.352 to 0.548, okay? So, somewhere in this gray area here, okay, in that box. Let's go back to our hypothesis test now. Notice what we were testing here. We were testing if P was greater than 40%. So what's in the null hypothesis? P is equal to 0.4, okay? So we were testing if P was equal to 0.4. Notice we can't eliminate it from being a possibility at this point, okay? Because what are we saying that with our confidence interval, what could P be equal to? Anywhere between 0.352 to 0.548. So we can't eliminate it, okay? But we're not saying that it's equal to 0.4, okay? Actually, what is our confidence interval is actually saying? It could be less than 0.4, right? So here are the numbers less than 0.4. It could be equal to 0.4, or it could be what? Greater than 0.4. And we don't know which one it is. Simple as that. We don't know which one it is, okay? So do you see how you cannot accept the null hypothesis as being 0.4? Because our confidence interval is telling us, well, it could be a little bit less than 0.4, it could be greater than 0.4, it could be equal to 0.4. We don't know which one, okay? So that's why we do not accept the null. Basically, what it's saying here is that everything's still plausible, okay? It could be less than 0.4, equal, greater. Well, let's do this. Instead of testing 0.4, let's say that we tested if P was equal to 0.2 versus greater than 0.2. All right. So 0.2 is right there. Okay. What's our possibility for values right now for the population portion P? It's still in the gray box, right? It's still the gray box. So is P being equal to 0.2 a possibility here based upon our confidence interval? The answer is no, it's not possible. Here we are extremely sure that P cannot equal 0.2, and that is what? It is greater than 0.2. It's because it's got to be somewhere, we're pretty sure, between 0.352 and 0.548 based upon our random sample that we conducted. Likewise, we could go to the opposite side of things and say that we tested if P was equal to 0.6 versus P is less than 0.6. So 0.6 is right here. Is that in our confidence interval? No. So it's not one of the possibilities for P. And we're pretty sure that P is going to be what? Less than 0.6, because it's going to be somewhere between 0.352 and 0.548. So notice we can eliminate now P being equal to 0.6. We're pretty sure it can't be anyways, okay? We're not absolutely sure, but we're pretty sure that P cannot be equal to 0.6 based upon our random sample, all right? So once we eliminate it, okay, that's telling us that the alternative is correct, or probably correct, okay? So this is why we cannot accept the null hypothesis, all right? And why we can reject it in other tests. So notice my subject here. Why can we reject the null in other tests? Okay, well, because we eliminated it as a possibility. All right, and so we get to reject it, and then we say, oh, okay, that means the alternative is correct. So other than a subtle difference in the standard error with P, meaning there's a little subtlety with regards to the standard error with regards to the confidence interval versus the hypothesis test. Okay. Other than that small subtlety, a confidence interval is the same as conducting a two-tailed test, and that is true for every parameter. So if you are going to construct a confidence interval, basically, you know what's going to happen with a two-tailed test then, all right? You know what the conclusion is going to be because now you have the set of numbers that P, or I shouldn't say P, but the parameter can equal. And now, so whatever hypothesis test that you run, you're pretty much going to know the conclusion. All right. All right. So in other words, if we went back to here we would have rejected the null. All right. This one we would have rejected the null. P is equal to 0.2. This one we would have said, oh, we do not reject the null because it is a possibility. Okay. And so that's what I mean is that you basically know what's going to happen with your hypothesis test then. All right. So a confidence interval is the same as conducting a two-tailed test. All right, so let's do this. Let's put it all together now. Now that we've talked about all the particulars here, let's just go through 3 examples, okay? And we'll go a little quicker, all right, as we go along, all right? And you'll see a left-tailed, right-tailed, and two-tailed test being run, all right? So we test if the percentage of all Ohio drivers that always wear their seatbelts while driving is less than 90% at an alpha of 0.1. So notice I can make alpha into a percentage or a decimal. We randomly select 200 Ohio drivers and 170 indicated that they always wear their seatbelts while driving. Okay, how do we know that we're conducting a hypothesis test? Well, once it says we test, okay, and that's pretty much telling you, okay, we're conducting a hypothesis test. We're not constructing a confidence interval. And the significance level was clearly stated. Okay. Variable. What was the underlying variable? Always wear a seatbelt while driving, right? Does a person always wear their seatbelt while driving? And it's categorical. And so you're going to either answer yes or no to that, right? Or every person is going to answer yes or no to that. And so it's the underlying variable is categorical. That means we're going to look at percentages or proportions. Okay. What was our sample? It was 200 Ohio drivers, n is equal to 200. That means our population is all Ohio drivers. What would be a success? Finding a person that always wear their seatbelt while driving. Number of successes, 170. That would be X. And so P hat would be 170 divided by 200 or 0.85. All right, or 85%, however you want to think of it. I put it as a decimal here because we're going to have to throw it into our test statistic like that. All right, so step 1, state the hypotheses. So I'm going to start with the alternative because that's what's usually stated in the problem. Notice we're testing if P is what? Less than 90%. All right, so I put, you can either put P as less than 0.9. That's what I tend to do. But if you wanted to put it as a percentage, that's fine too. P is less than 90%. What is the null? All right. And that means P sub 0 is equal to 0.9. So remember, the null hypothesis always has the equal. Step 2, check the conditions. Okay. So we need a random sample to be taken, or the data was obtained with an experiment. We did a random sample. Okay. So we randomly select. So we did our random sample, check. Moving on. We got to verify the central limit theorem. Okay. We got to verify that it applies and that the sampling distribution of p hat is approximately normal. So we can use the formula that I've been showing you. Now, there's be careful on this one because it's slightly different than for a hypothesis test versus a confidence interval for p. So we got to verify that at both n times p sub 0. So remember, we have an assumption for the value for p. We use it. We use it as much as we possibly can. So here we're going to be using it in our conditions. So we're going to verify that n times p sub 0 is greater than 10, greater than or equal to 10, and that n times 1 minus p sub 0 is greater than or equal to 10. So that's the conditions for a hypothesis test. Now I told you, remember that for a confidence interval, it would be n times p hat because we don't have an estimate for p sub 0, right? We don't have an assumption for it. And remember, that would just be equal to x. Well, n times p sub 0 does not equal x. And n times 1 minus p sub 0 doesn't equal n minus x, okay? And so we actually have to do the calculations here, all right? And so n times p sub 0, that n is 200, p sub 0 is 0.9, that we got 180. That's certainly greater than or equal to 10. We do it also n times, so notice here, n times 1 minus p sub 0 is 20. That's greater than or equal to 10. Check mark, check mark. We have the central limit there I'm applying, and the sampling distribution of p hat is what? Approximately normal. Once we have our conditions, we can use the formula that I've been showing you. Step 3, calculate the test stat. So let's go ahead and calculate the test stat. And there's our null and the alternative hypotheses again, with p sub 0 being equal to 0.9, because we're going to need that. P hat was 0.85 as a reminder. All right. And what did we come out with? I came out with a negative 2.36, and that's perfectly fine for Z. Remember, Z score can be negative. That's just telling us that P hat was what? Below the value in the null hypothesis. Notice P hat was 0.85, and that's below the value in the null, 0.9. So let's interpret that, that test statistic. So what that's telling us, that I did that right here. So interpretation of the test stat, the sample proportion p hat, our p hat was what? 2.37 standard errors below, because of the negative sign, below the value in the null hypothesis. All right, so p hat is 2.36 standard errors below the value of the null. Okay, what's next? Calculate the p-value, right? And so we have a left-tail test, right? We have a left-tail test. Here's our p-value. Okay, so what we did here, what I did is I started with the sampling distribution of p hat, and we would put 0.9 right smack dab in the center. Okay, and our standard error was basically 0.02, and so that's why I have basically 0.88, 0.86, 0.84. Okay, and our p hat turned out to be what? 0.85, which is right there, and we want the area to the left of it, but we have to, that in order to look up the p-value properly, though, we got to change it into a standard normal, right? And so there's our z-scores. And so notice that negative 2.36, okay? We got to figure out this area to the left of a negative 2.36. All right. All right, so let's go to step 5, which is our conclusion. And I got to get the presentation to catch up. So reminder, I keep on reminding you of this because this is important, right? P-value is less than alpha, we're going to reject. Do not reject if it's greater. Don't ever accept the null as being true. All right, P-value is pretty small, 0.0092. Is smaller than the significance level of 0.1. So what we're going to do, we're going to reject the null, and we think HA is correct. Okay, we think HA is correct. And remember what HA was? P was less than 90%, so we think it's less than 90%. So our conclusion, we have strong statistically significant evidence. This time I put at this 10% significance level. If you don't want to put that 10% significance level, I'm okay. That P is less than 90%, but that's not good enough, right? We don't want to just say that P is less than 90%. We got to put it in terms of, what did I say? We got to put it in terms of the problem. So what was P? Is the percentage of all Ohio drivers that consistently wear their seatbelts while driving. So we're pretty sure that that's less than 90%. I hope that's not the case, okay? But based upon my made-up numbers, there you go, okay? Because that was just a made-up problem, okay? Hopefully that that all made sense. All right, should we go to the next one? So a greetings card company such as Hallmark is concerned over the percentage of people that sends Christmas cards in the mail. Because, you know, a lot of people back in like the 60s, 70s, 80s, they sent a ton of Christmas cards, okay? But now with the internet and things like that, and easily connecting with people, maybe it's really died down, okay? And this is a concern for these companies. In order to turn a profit during the season, the company needs more than 50% of all households in the U.S. Still basically send Christmas cards in the mail. The company randomly selects 400 U.S. households and finds 80, still sends Christmas cards. Test at the 1% significance level, there's alpha. If more than 15% of all households in the U.S. still send Christmas cards. Okay. How do we know to conduct a hypothesis test? Well, it's a test and then gave it an alpha. Okay. What was the variable? Does a household still send Christmas cards? Yes, no, categorical. That means we're going to look at a percentage to analyze the stuff. What was our sample? Hopefully you said that was 400. N is equal to 400 here. That means our population was all US households. Success, finding a household that still sends Christmas cards, right? How many did we find sends Christmas cards still? 80. I'm sure they would gather more information than just this, but this would be a good start because they would have to find out then, well, on average, how many Christmas cards are these people sending? So maybe that's where they would head next. But anyways, let's figure this one out. So what's our sample proportion? It would be 80 out of 400 or 0.2, 20%. I just used easy numbers to go through this stuff. All right, so step one, state the hypotheses. So we wanted to test let me get my pen back out right here. Test the 1% significance level of more than 15%. Okay, and so that's what we're testing. That's in the alternative. P is greater than 15% or P is greater than 0.15. We go back to the null. P is equal to 0.15. That means P sub 0 is 0.15, right? We're going to see if that's a plausible value based upon our random sample and taking into consideration sampling error, okay? Normal sampling error. So this is a right tail test because we have a greater than sign. Okay, check the conditions. Random sample was taken, check mark. Verify the central limit theorem, all right? And I just remind you about the conditions for confidence interval versus a hypothesis test. Here, n times p sub 0, that's 500 times 0.15. I think if you did the math there, you got 60. That's greater than or equal to 10. Check mark. If you do the other calculation, you come out with 340. That's greater than or equal to 10. Check mark. So since both are greater than or equal to 10, CLT applies, and the sampling distribution of p hat is approximately normal. Good, we got our conditions. Calculate the test stat next. Right, here's our test stat. So just to remind you, here's the background information. I threw that into the formula. I got here 2.80. We should interpret that, right? So here's the interpretation. The sample proportion p hat is 2.80 standard errors above the value in the null hypothesis because we had a test statistic that was positive. All right. Calculate the p-value. There's our test stat. It's a right tail test. And there's our graph. And so I had StatCrunch go ahead and basically draw out the sampling distribution of p hat. There's the area that we're looking for. Okay. We temporarily assume the null is true. That's why we threw 0.15 smack dab right there in the middle. Okay. And remember, there's our we got to translate that into a z-score. So we'll put the z-axis underneath. All right, there's our p-value that we're trying to find. And so, knowing me, I didn't write down the p-value here in the presentation. So we got to look up greater than 2.80. All right, let's go ahead and do that. Let's go look up greater than 2.80. So we already know it's going to be 0.0026 because of symmetry, right? Because of symmetry, it's going to be 0.0026. But we looked up 2.80, took 1 minus that, same answer, right? 0.0026. Okay, here's our, we got to do the decision and conclusion. All right, so we had a p-value of 0.0026. That's less than 0.01. So we're going to reject the null. We think that the statement in the null is wrong and the alternative is correct. Okay, so we don't think that the value in the null is a plausible value for p. Okay, and the alternative we think is correct. Okay, so here's our conclusion. We have strong statistical evidence at the 1% significance level. So notice I changed it up a little bit there. Okay. Uh, you know, like I said, we're just trying to get the main points down. At the 1% significance level, that the percentage of all U.S. households that sends Christmas cards is more than 15%. So they may maybe conduct some more studies and say, okay, well, for the people, for the households that are sending Christmas cards, maybe on average, how many are sending, or how much you're going to spend, or I don't know, things like that. Okay. All right. One more, because we'll do a two-tailed test now. So an adoption agency wants to investigate if the proportion of all children that are adopted within 1 year after arriving has changed, tells us two-tailed. From 3 years ago when that proportion was 0.24. The agency randomly selects 150 children over the past 3 years and finds 45 were adopted within 1 year. Run this test at a significance level of 5%. So how do we know to conduct a hypothesis test? Same as before, okay? We said run this test, basically. What's the variable? Was a child adopted within 1 year after arriving, yes or no? Not all categorical variables are yes or no, but a lot of times when we do a hypothesis test, they are. So that's why we're looking at a percentage or a proportion. What was our sample? Looks like 150 children at this agency. That means n is equal to 150. Our population, all children at this agency. What would be a success? And this would be a really good success. Finding a child that was adopted with 1 year after arriving. Number of successes that we had, 45. That's x. X over n, that would be 0.3. Okay. All right, there's p hat. Now we got to compare that to the value in the null. So that means we have to set up the hypotheses. So we have p is not equal to 0.24 or 24%. And let's see here. P is equal to 0.24 or 24% for the null. That means p sub 0 is 0.24. This is a two-tailed test, and we are testing both less than and greater than at the same time. Check the conditions. We don't have any assumptions here. Random sample, check. Verify the central limit theorem, just reminding of stuff. All right. N times p sub 0, that turned out to be 36. That's greater than or equal to 10. Check mark. All right. Next one turns out to be 114. That calculation, that's greater than or equal to 10. Check mark. Since both greater than or equal to 10, the CLT applies, and the sampling distribution of p hat is approximately normal. Okay. Calculate the test stat. If you want to follow along, maybe do this stuff on, piece of paper and pencil along with me, fine. See if you can maybe pause the video here and start filling in some of the answers. Okay, see if you get what I get. So there's our background information. I fill in the numbers. Remember, we're using p sub 0 down here, okay, not p hat, okay? So when I say down here, okay, I mean in the standard error underneath the square root. Remember, it's p sub 0, not p hat. So I got here 1.72. What's the interpretation of that? The sample proportion p hat is 1.72 standard errors above the value in the null. And calculate the p-value. All right, two-tailed. So we got to be careful with this. So we got to combine those two tails together. It's kind of hard to draw this, get this to work perfectly in StatCrunch. I actually had to cut and paste and do some funky stuff here to get all this to work. That's why you got this break here, but good enough. Gets the point across. We got to combine these two tails together. And we got our z-axis down here, okay? And so let's see here, a negative 1.72. We got to look that one up. All right, let's go ahead and look that up. Negative 1.72. Negative 1.72. I got here 0.0427. Well, that's not our answer though. For our p-value, we've got to double that, right? We got to double that. So what do you get? 0.0854? 0.0854? That's what I get anyways when I double in my head. Okay, let's see what we got on the next slide. Oh, you know what? I'll tell you what happened here. I didn't make a mistake. I know exactly what I did. Let me get here. Let me just point something out to you guys. Is that I actually figured this out in StatCrunch. Okay, and StatCrunch takes it out, a lot more decimal places. And so if you accurately figure it out in StatCrunch, it actually turned out to be 0.0853. I would accept either one as an answer. Okay, StatCrunch, standard normal table. To me, it's just easier to look up on the standard normal tables really quick, and you multiply it by 2. It's good enough. Okay, who cares that it's off by 0.0001? That's not the point. The point is that that you got a close enough answer and you knew what you're doing. Okay, so that was not a mistake. That came out of StatCrunch. Okay. All right, moving on. Uh, that's greater than 0.05. So we would say what? Do not reject the null. Don't say do not reject and leave it like that. Do not reject what? Do not reject the null. Okay. So we think that the statement of the null and the alternative hypotheses are both still possible, right? They're still plausible. And actually, you can even extend that and say that, oh, well, actually, in this case, since it's two-tailed, that we got to actually kind of stop it there. So that basically the results are inconclusive, right? And we would say we do not have strong statistical evidence at the 5% significance level that the proportion of all children being adopted in the last 3 years has changed from 0.24. Okay, so we don't have significant evidence that it's either gone up or gone down. Okay, it probably has. Okay, it probably is different than 0.24. Okay, but we're not sure at this point based upon our random sample. Okay, so hopefully that explains everything. Okay, so thank you for your time. Eventually what we're going to be doing is testing what? Mu. Okay, we're going to change our parameter. Okay, that means our test stat's going to change. That means we're going to have to look on the t-table in order to look up our p-value versus the standard normal. Okay, and so on and so forth. Okay, all right. Thank you for your time today.